Hello, Shasta High School CP Math 1. This is Mr. Roberts, and here's a look at some of the answers to this evening's homework assignment. Um, Again, I caution you, if you're just kind of passively sitting and listening to these, this isn't really going to help you a lot, but I try to be thorough in my explanations for those of you that are really struggling or trying to get back into, uh, you know, a successful place in the course. But again, I do caution you that just sitting and passively listening is not magic here. You are the one who governs the gateway to your mind. I just hope that you help this finds you maybe helps you maybe find or strengthen neural pathways that make math more possible for you. Anyways, the first problem 134 asks us to solve 4 different systems of equations using any method, and it says to check each solution if possible. The very first one is, and I rewrote it down here below, is negative 2x plus 3y equals 1, and the other equation is 2x plus 6y equals 2. Well, I blink at this twice, and the way it's set up, it's in standard form, right? You can see the x's plus or minus some y's, and then equals a constant on the other side. And the x coefficients are exactly opposites of each other. You can see I've got a negative 2 and a positive 2 for the coefficients of x. So I immediately think I'm going to solve this with elimination. Essentially what I'm doing is I'm adding equal things to both sides of this equation, right? On the one hand, I'm going to add 2 to this side, and on the other hand, I'm going to add 2x plus 6y, which is equivalent to 2. Why do I know it's equivalent to 2? Well, because the second equation tells me it's equivalent to 2. So I have equal things, I'm adding equal things, therefore I will get equal things. And the equal things that I get are nice because x disappears. That's the term elimination, right? X is eliminated. So on the left-hand side, we've got simple 9y, and on the right-hand side, we've got the number 3. And if I divide both sides by 9, I get that y is 3/9, right? Divided by 3. Therefore, y is 1/3. So I know what y is. It's 1/3. I need to use this now to figure out what x is. And it doesn't matter which equation I can use, I can use either one. I'm going to go ahead and choose to use the first equation, the top one. So I'm rewriting that top equation. However, this time I'm going to replace y with what I just found y to be, right? So that top equation is going to become negative 2x and then plus 3 times, here's the y, 3 times 1/3, and that equals 1. Therefore, negative 2x plus 1 equals 1. If I take away 1 from both sides, be real careful here, I get negative 2x equals, something's got to go there. What's going to go there? Well, I'm taking away 1 from each side. What goes there is the number 0. And yeah, if I divide both sides of this by negative 2, I do get that x is 0 divided by negative 2 is 0. So my solution is the point x is 0, y is 1/3. X is 0, y is 1/3. Now, the problem did say check this if possible. So let's go ahead and check this one using our calculator. So I'm going to plug in what I found for x and y in the left-hand side. Of the first equation, I should get 1, and when I plug what I found for x and y in the second equation into the left-hand side, I should get 2. And if I get the 1 and if I get the 2, then it does check. So the first equation, 0. Negative 2 times 0 is just 0, so I get 3 times 1/3. You know what? I don't need a calculator, right? 3 times 1/3 is clearly going to be the number 1, right? That's 1/3 plus 1/3 plus 1/3. 3 1/3 is the number 1. And then 6 1/3, right? 6 times 1/3 is going to be the number 2. And if you want, you can write 6 times 1/3, which is what? It's 6/3, which is clearly the number 2. So it definitely, most definitely checks, right? Let's go on to B. So I did rewrite B, and I always like to kind of just look at it and let my eyes flit back and forth to make sure that I've got it exactly as it was. But I do see y equals 1/3 times x plus 4, and then x equals negative 3 times y. Well, this is a great example of a situation where I would choose to use substitution. The second equation says that this thing right here, negative 3y, is a valid substitution for x. So I'm going to rewrite that top equation, but instead of x, I'm going to use negative 3y. So this equation, the top one, would become y equals positive 1/3 times a negative 3y and then plus 4. Well, when I multiply this negative 1/3, or positive 1/3 rather, times negative 3, I get negative 1. 1/3 times negative 3 is negative 1. So that gives me y equals negative y plus 4. Now, when you get to a point where things are looking like this, don't jump to conclusions. Slow down and look at what's going on here, right? If I want to solve for y, I'm going to add y to both sides. I do not have the same y's on each side. On one side, I've got a positive y, and the other side, I have negative y. So I'm going to add y to each side. When I add y to the right-hand side, you can see I've got a negative y and a positive y. That equals 0y over on the right-hand side. And then don't forget there's a 4. So this becomes 4 on the right-hand side, and on the left-hand side, we've got 2 y's. Well, if I divide both sides by 2, we get that y would be the number 2. So y is 2 is part of our solution. And then to figure out what x is, that second equation is perfect, right? It says, hey, x should be negative 3 times the number 2. Therefore, x should be the number negative 6. So my solution is the two of these together, right? I should write it as an ordered pair. Negative 6 comma 2 is my solution point. And I don't really need to check it with the second equation because I just did that. That's how I got the negative 6 out of it. But let's plug it into the first equation. If I take 1/3 times negative 6, and you know what, I will do this with the calculator, although the arithmetic's pretty simple. I'll do 1/3, there's 1/3, and I'm going to multiply that by the number negative 6, so the opposite of 6. Again, I'm using this button down here on the bottom right with the negative on it. That's negative 6. And then I'm going to just add 4 to that, plus 4. And when I press equals, I should get y. I should get the number 2. And you can see I do get 2. So when I fed 6 into that equation, it produced an output of 2 for y. So it totally checks. Let's move on to C. So here's C, and I'm reading it to myself again from the book to make sure I wrote down the correct thing. But it is a 3x minus y equals 7. The other equation is y equals 3x minus 2. This looks like substitution, again, because the second equation tells me that this is equivalent to y, right? Y can be thought of as 3x minus 2 for this system. So I'm going to plug that value of y into the first equation. So let's rewrite the first equation. It's going to become 3 times x minus, and then I open parentheses. In the place of the parentheses, I'm going to place y, which is 3x and minus 2, and that equals the value 7. Now there is this negative symbol that needs to be distributed, right? I'm subtracting all of this. So it's helpful, I think, to think about this as a negative 1 times this, but I need to make sure I push through this negative 1 factor to both of these terms sitting inside the parentheses, right? The 3x term and the negative 2 term both need this factor of negative 1. So I'm going to multiply both of them by negative 1. This would become a 3x, and then minus 3x, and then plus 2, and that equals 7. That's interesting because 3x and negative 3x is 0, so I just got that 2 is the number 7. So this right here is obviously a contradiction. This is not true. And this is the kind of thing that happens when we end up getting a system of equations in which we're looking at parallel lines, right? There's lines that don't have an intersection at all. So I want to take a look at that graphically. So I think you can just see our system of equations just off to the left there. So it was 3 times x. So let me hit 3x. Oops, input. So 3x. And then I'm going to subtract from that y. So 3x minus y. And that should equal the number 7. So here's the first of 2 equations. Oops. 3x minus y equals 7. And then the other equation is y equals 3x minus 2. So let's type y equals Oops. So there's y equals 3x minus 2, and let me enter that. And they certainly do, appear to be parallel to each other. I wouldn't say that, being parallel is guaranteed just by the look of it. But one of the things that GeoGebra does do easily is it allows me to measure slopes of lines. So if I come in here, this is the measurement menu, and you can see one of the options is to measure slope. So if I hit this line and this line, it gave me two different slope triangles there, and did a very nice job, right? You can see that there's a interesting that they put it on this side, right? They're showing a rise of -3 and a run of -1. But, -3 over -1 is still +3. Both of them have slopes of +3. You can see there's the top line and that's the other line. So whenever you end up with slopes of lines that are equal to each other, we know that these lines are parallel. So they don't intersect at all. And that's why we end up getting this contradiction. 2 is not the number 7. So we would just conclude by saying there's no solution here. And for our final system, we've got x plus 2y equals 1 and 3x plus 5y equals 8. Again, the reason why I was reading that is I was just checking the book and making sure I copied this correctly, because oftentimes that can be a mistake, is just not transcribing something correctly. This problem would probably work well with substitution or elimination. If I wanted to, I could clearly rewrite this so that x was alone in the first equation, right? I could get that alone by subtracting 2y, and then I could substitute. Or I could choose to, and I think I'm going to go this way with this one. I'm going to multiply both sides of this equation, the top equation, by -3. So if I multiply both the left-hand side and the right-hand side by -3, what I'm going to do is create a situation where my x coefficients will be opposites of each other, and I can use elimination. So let's just rewrite this problem now as we push a factor of 3 to each one of its terms. Over on the left-hand side, we end up with -3x, and then by pushing that -3 factor, I get a -6y, and on the other side, that equals -3. So that's what that becomes. After I take the equal things and I multiply by equal things, I get things that are equal as well. So this is still a true statement for this system. I haven't changed anything. For the second equation, I'm just going to transcribe it. It's a 3x plus 5y, and that equals 8, exactly as it was before. And now I'm going to go ahead and use this method of elimination. I'm adding equal things to each side of the original equation. On the one side, I'm going to add this 8, right? I'm going to add 8 to this side. And the thing that's equivalent to 8, according to this equation, is 3x plus 5y. So I'm going to add that to both sides. So it's really important. I want you to understand the logic of this, right? This isn't some magic series of hoops we're going through. The top equation tells me that -3x minus 6y is -3. They're equivalent. The bottom equation tells me two other things are equivalent. Well, if I take that top equation with the blue equal sign and I add equal things to both sides of it, I get equal things. Equal things plus equal things yields equal things, equal quantities. So over on the left-hand side, when I combine -3 and 8, we do get a +5. And over on the left-hand side, the -3x and the 3x cancel. That was by design. That was our whole strategy. And then finally, I get a -y left over, right? So -y is equal to 5. And let's go ahead and push that forward. If that's the case, and I divide both sides or multiply both sides by -1, we get that y would be -5. So we know what y is, right? Y is -5. Let's use that to figure out what x is. I'm just going to plug this into the second equation. The numbers might be slightly larger, but I can handle it. So there's a 3x and then plus 5 times, but playing the part of y, we now believe that y is -5, and that equals 8. So 3x minus 25 is 8. If I add 25 to both sides, we get that 3x equals, well, that's nice. It'll be divisible. We get 33. And finally, if I divide both sides of that by 3, I do get that x is the number 11. So our solution is, let's see, 11 comma negative 5. 11 negative 5. And you know what? For that one, I think, how are we going to check it? Let's just check it by plugging that in. So in the top equation, I've got an x, so that's negative 5. Oh, yep. And then plus 2. Oh no, x is 11, my bad. So x is 11, so I've got 11, there's the x, and then plus 2 times negative 5, well that's negative 10, so I get 11 minus 10, which is indeed 1, because that's what the equation said it should be. So it definitely checks in the first equation. On the second equation, 3 times x would be 33, and then plus 5 times y, that would be plus a negative 25. And yeah, when I take 33 and I subtract 25, I do indeed get 8. So it made both sides equal 8. So that's the final one for the first question. We used mostly elimination and one instance of substitution here.